Yeah, I think you can connect the beforehand. So, because they have this thing that you might yeah, I see that. Right, you can just how you can over the person, you can just are you going to present using your laptop? Or do you want to send it your you don't have to connect or just log into your just need a browser to go to that. Just tell you where you're going. Oh, you have the all of the yeah, we can already okay. That also works. No, I don't have to. Okay. No, I'll send you. I don't have to figure out all the time. Those guys are actually.
It's hard. Yeah, I'm just trying to figure out like
You can bring it out.
trying to see if we can duplicate the
No,
All of AWS?
no, I'm not. I'm good at cloud. I'm more of the. This is,
use as stop. It is mirroring, but then when I go to but I don't know if the folks online are seeing that or the note screen. Yeah. And
Can you ask?
someone else has asked like presentation mode doesn't let me go back to Zoom. So if someone else can dial in. Can you dial in to Zoom? I'm trying to see.
Most of my thesis is based on AWS great solving
Are you on Zoom? Yeah, are you on Zoom or? Okay, can you confirm if you see like this screen or you see the notes? Oh, you see this one? Okay. Okay, we're good to go then.
All right, okay, so we have our first presentation of this afternoon, and it's from AWS by Shreyas and Virgie. So they will talk about smaller models can pack a punch in the area of large language models. All right.
Thanks so much for the opportunity to present. So my name is Shreyas Subramanian. Thanks for coming and choosing our session. We'll try to make it interesting. I'm joined by Majid. Both of us work for Amazon Web Services. We're working with AWS AI ML customers. Today, we're kind of talking about like an unpopular opinion of why smaller models can actually do quite a good job in multiple tasks when the rest of the world, including us, we spend most of our time on large language models and other large foundational models, right? Quick agenda. We'll go through some kind of basics, including scaling laws and kind of the investment that customers of AWS and Google and Microsoft, all of them combined, really have to invest in when they have to do large language model training and hosting. We'll talk about a few like case studies that are interesting, comparing smaller models with larger models. We'll talk about a few techniques that can be used to create these smaller, more competitive, smaller models, and then we'll end with some really cool like applications of smaller language models, right? For the folks online, yeah, let me know if I should speak louder or if you can't see the screen, and someone here will. Oh, sure. Thanks. So we're in this journey of exploring large foundational models. This one's going to be specifically about large language models, and we're kind of wondering where are the 1 trillion models and the multiple trillion models. One kind of insight that we can get is from the scaling laws, and these scaling laws essentially are just like a function fit equation. They did a bunch of experiments and are trying to figure out what is the relationship between the amount of data you have and the model parameter size, and in an ideal world, how much data should you train a particular model with, right? What do you see on the equation? I won't spend too much time on the equation, but essentially there's two main parameters. There's the number of model parameters n, which is in red, and then the amount of data that you have, right? The number of model parameters currently, if you're talking about large language models, it's in the billions of parameters. And with data, it's usually in the trillions of tokens, right? So that's kind of the scale at which we're operating. The interesting thing is you can kind of train equal performing models which are smaller but are trained with larger amounts of data, or larger models that are trained with smaller amount of data. And usually the effort in terms of money or cost or time is kind of the same. So you'll see that in the black kind of dotted line. The chinchilla model, which the scaling law is based on, it's about a 70 billion parameter model. In today's scale, that's not a huge model, right? So we just saw in the NVIDIA release of 540 billion parameter model. It was trained with a lot of data though, so about 1.4 trillion tokens of data. If you follow that contour, which is kind of like an ISO performance contour, so any model that you meet along that black dotted line should have typically the same kind of performance. We kind of meet the Palm model there. The Palm model is much larger. So it's 540 billion parameters, but it's trained with small amount of data. And roughly the performance over multiple tasks is the same, right? What you can't see in the bottom left there are just smaller models, but they're also trained with smaller amount of data, so they don't perform as well, right? So that's not really exciting. So what would you need if you had to train your own competitive large language model, right? So there's the main scaling equation. It has factors that depend on the number of parameters, the red parameter that we saw in the previous slide, the amount of data. And you can kind of figure out what kind of cluster you would need on a cloud like AWS or Azure or Google, right? So let's assume you want to train a model and you're doing it in full float 16. You're not kind of taking shortcuts. You're not doing like an integer version of the model. What would be the size of a 1 trillion parameter size of a cluster for a 1 trillion parameter model and a 1 trillion data set size, right? So if you go through that equation, and we'll skip the graphs for now, but essentially that shows that the scaling law is good, it works. So what you'll see is that if you want to train a 1 trillion parameter model with 1 trillion tokens, and you have a time budget, you can't just keep going on forever, and you want to do it within like a quarter or 100 days, you would need about 2,225 GPUs of the highest quality on AWS or anywhere else that you can find the GPU. And that equates to about $21 million. So if you have 21 or more $1 million lying around, you can kind of get down into the investment of building these large language models. So our talk really is about, can smaller models, which are more efficient, can be hosted and trained with fewer resources and smaller like a bank balance, can those be competent enough for us to use in multiple use cases, right? So Majid and I were doing, we're kind of passionate about this topic, and we're actually writing a survey paper on this. One of the things that we have is this idea of like an equivalent size, right? So if you're dealing with a 7 billion parameter model, can it perform as well as a 70 billion parameter model or a 500 billion parameter model on certain benchmarks, right? So if it can beat or perform at the same level as a larger model, then we kind of say that the 7 billion parameter model has an equivalent size of 500 billion, right? So the blue graph, the blue lines that you see, or the blue bar charts that you see, is kind of how do you extend that capability of a small model. Some of these that you may have heard of, the fee models from Microsoft, or stable code from Stability AI. You'll see that the orange graph is the actual performance, but it's also equivalent performance to a much larger model. This is kind of in log scale. So it looks a little bit compressed, but in the full realization of this and not log scale, you'll see some impressive capabilities for these smaller models. So practically, like, what are you paying for, right? So what you see on the y-axis is kind of a general quality index. It comes from interacting with a model as though it was like a chat bot. People get to vote on it, and then and it's kind of a blind vote, so you don't know what you're chatting with, but you kind of vote on which performs better. You could do benchmarks as well, and the benchmarks, like a picture, if you change the y-axis to benchmarks, is not very different. So this is, understand, like the y-axis is kind of quality, x-axis is how much you pay for it, right? So you want to be really in the top left in the green area there. So you want to pay very less, but you want a really high quality of the model. And you'll see that some of these small models, like the Mistral Small, for example, or Gemini 1.5 Flash, all of those are really small models. They perform really well. Like the speed at which they can output tokens is really high compared to some of the larger models. You will have like a competitive choice of models that you pay very less for, but are very competitive to use in multiple tasks. These are not models that are typical in what we saw about 10 years back with NLP, and here's a model that we fine-tuned just for classification or sentiment analysis. These are still general purpose models. You can prompt them to do what you want, and you can also fine-tune them, right? So it's getting interesting there. I also think, funnily enough, like a lot of the folks that are working on the smaller models, they will tend to annoy the larger folks in the room, because Claude Sonnet 3.5, or forget about the top right, which is Opus, extremely expensive, but has a decent quality. But if Mistral Small can come up to, again, back to that equivalent size, if it's performing at a much higher level for much cheaper, because you can host it for cheaper, it becomes really interesting for people who are actually spending money. So we'll go through quickly like a few interesting like models that we want to highlight, starting with Mistral 7B. Mistral is a startup that came up into the scene like a year ago, and they have like a bunch of models right now, starting off with open source, and now they have some commercial models as well. In like the architecture of a Mistral model is similar to Llama model, which you have heard of. It has some small modifications to it, and that makes it kind of slightly better. And this is another view of like that equivalent size, right? So we'll look at one of these, which is like a reasoning ability on the right. You'll see that like Mistral, which is when compared to Llama, it has maybe an effective size of about 38 billion parameters, despite being only 7 billion parameters. It means it's performing at roughly 38 billion scale when you look at the benchmark for reasoning. Similar things happen when you look at other benchmarks, and if you kind of aggregate that out, you're getting a lot of punch out of this Mistral series of models, right? So people took that Mistral model and kind of modified it down, with more data, with alignment and feedback from preference data. So you'll see that Mistral AI, as they continue going from the Mistral 7B to the Mistral Small, Now the Mistral Small is faster and cheaper to use and performs better than Mistral 7B. Similarly, on the commercial world as well as open source, you have models like the Zephyr model and the Notice, which you'll see slowly start kind of aggregating a bag of tricks that will get them to perform better than the base Mistral model. Another interesting one is Orca, which is another series of models. It can be used for general text tasks. One of the things that they evaluated against is so you have two series of models. You have Orca 1 and Orca 2, and you have all of these on the bottom right. Again, you have all of these models. The leftmost bar on this graph here is GPT-4, right? So think of that as kind of the North Star for some of these smaller models. You'll see that Orca is kind of third in that line. So there's GPT-4, ChatGPT, which is believed to be GPT 3.5, and some combination of other things. Now probably is GPT 4.0. And then Orca, which is a 13 billion parameter model, performs as good as ChatGPT. So if you didn't know what you're chatting with, you would kind of randomly choose between ChatGPT and Orca if you were to vote on it, right? Another one that Majid and I both are like personally very interested in is the Phi series of models from Microsoft. So they really focused on really high quality data, right? So now we're kind of breaking the equation of the scaling laws, where if you have small amount of data, but then it's really highly curated, and you're filtering out all of the noise or deduplicating. They call their paper textbooks are all you need, because textbooks usually have like high quality data, and that's what they mean by it. I don't think they purely trained on textbooks. So if you had like really high quality data, but you still have smaller amount of data, you still get effectively a much higher quality of a model. Phi models are extremely small, so they're 1 billion parameters in size, still perform great at reasoning and general ability, math, and question answering. Most recently, they released the Phi 3 Mini, which can be run on a phone. And the Phi 3 Mini actually beats all of the previous series of models that we talked about. It's about 4 GB of memory that you take. And if you compare that to if you're running Zoom on your browser or Slack on your browser, it's kind of similar, right? It's almost like running like an application on your browser. You can run that close to real time. You're not actually hosting it on the cloud. So this is super interesting for multiple people to look at. So changing gears a little bit, if you're kind of sold on the fact that small language models can be effective for your tasks, how do you actually build this? One of the easiest ways to build this is you take a large model and then post-training, you quantize it. And for those of you who are in the know, kind of, this is an easy process. In general, you have, all of these weights. You take the maximum value in those weights, you scale the weights by that value, and you kind of round off to an integer, right? So that's the general idea of quantization. And what that means is you still have the same number of parameters, but it takes less memory to kind of store in a GPU, right? So effectively smaller model in terms of like the GBs, gigabytes of storage space in a memory, but the number of parameters wise is the same. So this is easy to do. But the problem is that if you look at the top left image there, some of these are extremely noisy. So you'll see those peaks. If you took one of those red peaks and you scaled that tensor down by that peak, everything else would be 0, and you would see 3 rows of ones there, right? So this is not effective. You'll actually lose a lot of accuracy in your model quantization bit. So you have nice techniques like smooth quant, which basically shift your quantization difficulty from the weights to the activations, and they have like a hyperparameter that can kind of balance that out. Essentially, what it's doing is it's not losing a lot of information while quantizing. And this is again, you can do this post training. And what you see on the rightmost figure there is you're not losing a lot of information, but you still effectively quantize the model. Results wise, you'll see that the smooth quant version of certain models, and they went up to, I think, the OPT models, but the smooth quant version of those models perform as well as the FP16 versions, which is effectively full float. No one really uses FP32, but FP16 version you see that on a particular set of tasks, it'll see 69% performance. And then with the smooth quant version, you actually see slightly higher performance. So ignore the slightly higher performance for a bit. You can just kind of consider that as equivalent performance, right? So it's really interesting because now you can have 1.5x speed up and 2x, almost 2x memory saving. So you can kind of host it on a smaller GPU if you had to. And these are some other benchmarks just to show that it operates across multiple types of models, right? So you have the OPT 13 billion parameter model and the 30 billion parameter model, and you'll see that smooth quant does comparatively really well when you go against the FP16 full float model. So the idea is you want to retain all of the accuracy, but you want to store it with less memory, and that's what methods like smooth quant do. There's another nice, interesting method where that's kind of coming up in the last 6 months or so, where you can merge multiple models. The naive way of merging it generally doesn't work, right? So if you just kind of average the weights of two models that were fine-tuned with different data sets, it's going to do badly in those two data sets as a whole. And so that's called model weight averaging or model soup. But there are multiple other techniques that have come up. You can do like a spherical merging. You can use task arithmetic, which is basically saying like, how do I not lose capabilities of the original models in the merged model, right? So the merged model should perform well at the original tasks as well as perform overall better than the individual models. And you'll see all of you don't have to read the actual text on there, but essentially this is a list of models. The black line that goes through that list of that set of bar graphs is the size of the models, right? So you'll see some smaller models that are performing better than larger models just because they were merged from other highly capable models. The ones that are highlighted in the darker version of the pink are using this open source toolkit called MergeKit. And so this is from MergeKit's paper. So this is a really interesting way of doing things. You just have to choose a method, look at a leaderboard of models, and you can kind of merge it, save it as your own model, and it's likely going to do better than any of those individual models. So interesting way to, yeah. Yeah. So far all of these models, the same parameters, same architecture, but the merge kit is basically going to be modified to get any like different kinds of architectures, different types of number of parameters as well. So there's methods to do that. It's unclear like what the advantage would be if you don't know what the number of parameters is going to be. Like no one really knows if you can merge the capabilities of a larger model into a smaller model with smaller number of parameters, but it's something that's being worked on. Yeah. Another question? Yeah.
Do you see any work happening in offloading some of these merging capabilities to CPU, or is it more GPU exclusive? Can these small models, like at least the inferencing capabilities, can it run on certain high-end CPUs rather than
Yeah.
for 100?
Yeah, for those online, the question is like, can you run these merge models on CPUs, if I'm kind of paraphrasing that right? So the process of merging, you can do that on a CPU. It'll take a while longer, but usually it's done on a GPU because you want to, load up both those models or any n number of models and do that quickly. It's a fraction of the time, a really insignificant fraction of the time that it takes to fine tune your own model. I mean, I'm talking about if you have like 7 billion parameter models, it's going to take you a minute to merge those into something that's better. When it comes to actual inferencing, again, there's ways to do that on a CPU, generally slower, or on a GPU as well. And GPUs are, at least the ones that can host these smaller models, they come at a very competitive price. So you're kind of getting what you pay for in terms of performance. Usually no one does that on a CPU. There are some startups, Majid and I have met that basically try to do that with a really hyper quantized int4 model on a GPU or on a web GPU, basically that runs on the browser and using Intel CPUs. And I don't think that's kind of mainstream yet, but there is work on that.
In one direction, all the hardware providers are going for is neural processing units, which are
highly advanced for, small devices like laptops, then that's meant to host these type of models. Has better capabilities than a normal CPU, but not as expensive as a GPU.
Yeah, we are exploring certain opportunities where, like, cost versus performance versus security.
Yeah.
GPUs are still expensive. If I am not owning the hardware, if I'm using the hardware, I have to charge back to my customers some amount of dollar there. And customers are really not gonna pay for GPU. So there are explorations that are happening. Can we like have these, like as I mentioned, like info models or maybe smaller versions of these models? Can these models be uploaded on a mobile architecture?
So yeah, some of these models like the P3 Mini, like their entire pitch on their paper is that they ran their tests on iPhone. I mean, some tests on iPhone. Even that was kind of a quantized version of P3 Mini, but you could do certain tasks that you can do it privately, right? So there's no API call to the cloud or anything. It's just kind of a local model in that sense. But yeah, moving on, I think Majid can come up and we can talk about a couple of more techniques of kind of coming up with these smaller language models and a specific application as well.
Serious. All right. So moving on from the kind of like the techniques, this is another technique which is essentially based out of using much larger model to further quantize to smaller bits. So in this case, for Gemini series, when they came out, it was 3 different series: Gemini Ultra, Pro, and Nano. So Pro and Ultra, they had, of course, have larger context windows, have larger parameter sizes. And the purpose in this Gemini Nano is to kind of get as good as a performance, but also train it on a very dense data. So this was trained on a 1 trillion, somewhere about 1 trillion parameter token. And it was 2 different lengths, so 1.8 and 3.25, on a 4-bit quantization technique. And the purpose overall in this experiment is to achieve as good as Gemini Pro. So in these tasks, as you can see, common techniques, the Gemini Nano is performing almost 90% as accurate as a Gemini Pro. So the value prop is basically here, we could essentially use, these smaller models for let's say tasks like summarization, tasks like, simple RAG retrieval purposes, etc. And in some of these tasks, like translations, the ability of the Gemini Nano is 5% smaller than GPT-4. So think of this use case where, you have like privacy concerns. You can essentially host this type of a small model on a private environment, and that will perform as good as the GPT-4, whereas you're not bound with, let's say, token-based pricing, or you're not bound with any legal restrictions, etc. So as the paper that Shreyas was mentioning, we're essentially working on, defining these language models in different subsegments, like task-specific segments, task-agnostic segments. And in the case of, task specifics, you'll essentially see a lot of these, small language models coming out for, meta reasoning capabilities, which are very good when you fine-tune on specific use cases. Or things like, let's say a specific domain. So if you were to fine-tune a small language model on a specific domain like, astronomy, biology, the models are going to be performing way better than GPT-4 or other larger counterparts. So another sort of like a big shift that we're foreseeing, both from the industry as well as, the kind of like in the research areas, the small language models are very useful if you were to incorporate them with multi-LoRa settings. So in this case, if you were to compare, the purpose of the LoRa is we're trying to get the model as close to as the fine-tuning settings with using LoRa techniques, but using smaller amount of the, the required parameter fine-tuning. So with multi-LoRa, we can essentially outperform the LoRa. And the idea here is, think of a use case where you have, multiple different tasks you might have. So, and that task is something you're going to use for your LLM. And you can create multi-LoRa for your base LLM. So every time, let's say you have a specific task that comes in handy, you can offload. You can sort of like pull in the right LoRa from the base model, and this essentially helps you save from the overall memory concept. So instead of having 10 different, let's say, base model weights, you essentially have smaller LoRa weights that's available, and you use the base model, and then depending on the task, you switch between the different LoRa weights. And that's a specific direction we're kind of like leading towards with using tools that I will mention. Things like SageMaker is essentially supporting this inbuilt already, which you could use a one base model with multiple different LoRa's that is hosted from one GPU instance. So so far we mainly talk about the foundation models perspective, from the SLMs and how to create the SLMs. Now, how do you go from this to industry, and then create a case for a specific application for customers to think about? So here is very simple use case. It's a text to SQL. So the idea of this use case is basically you have a user. A user could be a coder. A user could be an analyst. It could be any type of persona, and then it's asking a question to a database, and that database is in a simple RAG-based architecture. It's just a simple retrievable, but most of the industry has SQL-based or NoSQL-based databases, and you still want to have a sort of a analysis out of or information retrieved from that specific database. So we use a foundation model here to create a SQL query in between, and then run that SQL query on the database, capture that information, and then output as a text or as a visualization to the end user. So how would that work? From a sort of a simple architecture, like with this architecture, you would pick an LLM, either through Hugging Face, all the other model providers, and then you define a simple template. In that simple template, you provide, this table schema that's available, and then every time there is a question asked, then you retrieve a SQL query, and then you write something, a wrapper like this, a DB SQL chain, and then that is run on your database. So it's as easy as this to sort of like implement. Even though kind of like I make it look very easy, this is actually a hard problem to solve because of all these technical sort of like complexities that's available. So first off, the table names, it could be codified. So if you were to look at a big enterprise, they have, thousands of different table names, which is codified based on the company's, instructions. You could have, cardinality, so which means you might have some schema mapping between different tables across, different tables. And it could provide kind of like a throwing key relationships. So you have different table names, and those table names are intercorrelated with the other tables that's available. You might have different industry terminology when you're talking to sort of like talking to your chatbot. So the chatbot should be able to understand that terminology. And you also might need to think about, the modalities. Are you looking to create a simple chatbot, or are you looking for LLM to simply create you the SQL query? And then end-to-end, we also need to think about the security. So why? Because think of this use case, you build it, you have the database, you're serving to any type of customer, and then you don't want, let's say, a bogus, to come in and do any changes on your databases. So you need to put some guardrails and some security at hand. And you also need to maybe think about, not giving any essential or confidential information to the user who doesn't have that privilege. So here is a simple demo where we built this demo on a Chinook database. It's a very small database. So every time you ask a question, just like this, it creates the SQL query, runs that SQL query, and then provides the answer. So it was how many tracks are there in the database, and what's the name of the employee. So this is another task which we kind of like enhance this, which is a plot. So it both create the SQL query, since this is a plotting task after, the information is retrieved, then it uses another SLM to create a Python function, and that Python function is run to create this simple visualization. So you can think about using SLM to do multiple different tasks in an agenting concept. So where is this going? We're seeing, a lot of services trying to, or already in their roadmap to incorporate this. So Redshift, which is something you might be familiar, it's one of the databases in AWS, which is mostly popular to use. It already has this incorporated using the Amazon, provided LLMs. So as part of your, chatbot interface, you simply sort of like ask the LLM to your database, and it provides you the SQL query right away. And then you could, insert this SQL query into the notebook, and then you could run it directly. Or, for customers who's not, targeted in this space, like QuickSight is also another experience where you simply connect multiple different databases. And then in the backend of this engine, it runs, whatever I did early on. And then provides you the plot, provides you all the text that's required, etc. Again, these are becoming more and more, built-in concepts, but it's not addressing for everybody, right? So if you were to solve this problem by yourself, you're going to have to think about how do you sort of like create a model, an SLM that is going to be performing as good as a larger model, but also you need to kind of like have the ability to fine-tune these SLMs. So there are some public benchmarks available in this space, Spider, WikiSQL, BERT, which are kind of like mostly known. And the recommended or the tested models that we did so far was StarCoder, SQL Coder, Wizard Coder, and Cloud3. And when you're kind of like doing this experimentation, then you're going to run into this, this triangle of decision, which is essentially quality, cost, and performance. So I will talk about sort of like a simple example that we did to showcase, this triangle of decision. But the idea here is simply how do I get a business value as low cost as possible and provide this to any type of, customer. So here is one example. As I kind of like in my slide as stated, we expect the fine-tuned models to be performing better than their base models. So in this example, Wizard Coder 15 billion parameter model, we are fine-tuned using a Spider Dev benchmark database. As you can see, the blue charts are basically the fine-tuned versions, and it is performing better than the base model itself. So the idea here, is fine-tune a model on a specific task, and then maybe use techniques like, quantization, like QLoRa, etc., to smaller the footprint of the memory for hosting. So that's one way to go. Now let's take a look at this, and compare this with a much larger context. So this was a little old study, so which is why the ChatGPT that was used here is ChatGPT GPT-4, and versus Claude version 1. Versus the fine-tuned version of the Wizard Coder. So as you can see, Claude or GPT-4, they're actually much more billion parameter models, versus fine-tuned Wizard Coder is essentially at the 15 billion parameter range. So as you can see, it is actually performing as good or on par with the other much larger models. So now with the new models, we did a similar study again. So this is on Llama 3 8 billion parameter model. So we're essentially comparing the Llama 3 8 billion parameter model on different types of prompt techniques. So the idea here is we simply use the base model, Llama 3 8 billion model, on Spider Dev benchmark datasets, and then do some prompt engineering techniques to improve the performance. So if you, let's say, provide a couple of sample rows as part of your prompt, then it gets better performance. And then if you fine-tune that model, then you actually get like way better performance than Llama 3 70 billion parameter model. So as you can see, there's a huge difference between the two, but you have better performance. And the required memory for this 8 billion parameter model is essentially something you could fit on a G5 to X large, which is essentially a 1 GPU based instance on Amazon. And if you were to do that same thing, on a required, GPU on the other side, it will cost you more than 10x. So that's essentially the value prop here for the SLMs. Basically, fine tune an SLM to do a certain level task and host it for your, for your training purposes. There is actually a lot more work in this space, so I will quickly bypass here because of the time. But simply, you can essentially do a lot more on your prompt template to get, let's say, dynamic few shot samples. So instead of doing, the same samples, you could have a knowledge base, and that knowledge base could have multiple different examples from your own data sets. And that's something you could use to improve the performance of the LLM. So this is another study. Basically, it's showing the default SQL coder versus GPT-4. And in different settings, as you can see, the smaller models are still performing very better on, these task segments. So simply, we talk a lot about, the foundation models, how you can access is two options at AWS right now. So Bedrock is serverless, API based. We have all these models that you can simply sign up and get an access directly. If you're interested in, fine tuning an open source model, SageMaker would be your go-to place where you can self-host, fine tune these models and then serve it for your application. With that said, that's all. Any questions for us? Yes.
Or relational databases only, or would it be the two graph databases as well?
Okay, so with the basically you could essentially do whatever I did for any other databases, but you will need sort of like a labeled data, which is why I was referring to those benchmarks. And now I see one direction. Essentially, that's not still enough. Where in the industry, there is like new tools coming out for, just for the sake of consideration. Basically, the idea here is you come as a customer and using that tool, you build spider dev like benchmark data sets and use that when you're fine tuning the model. So you can essentially go from like the data is the most important aspect. When you get a better data, then you can do pretty much everything with small language models. Yes. Yes, the database schema. Yeah.
So you're trying to generate SQL here. So for a graph database, you might generate like a Gremlin.
Gremlin, yes.
And finding on that data set should do better.
I have a question. And so the smallest model in your slides are also billion parameters.
Mhm.
So do you see in the near future we're going to have several hundred million parameter good performing models, just like a bird but more powerful than bird?
In our survey paper, we have a couple of them. The thing about them is it's on like task specific concepts, like let's say writing an Excel code. So a model like in the range of I believe 100 million to 300 million is very performing better than ChatGPT in those concepts, but not in the case of, let's say, text to SQL.
So
Yeah.
these ones are all like general purpose, meaning it can be prompted to do multiple tasks. But essentially, you could go down like 10 million, 50 million parameters, fine tune a debugger model to do classification better than any of us.
Yeah.
Maybe.
Yes, I think so.
Any other questions?
Thank you, guys.
Thank you.
About admission, question.
Yeah,
Sure.
sure.
So how do you measure the like comparing